All right, hello everyone. This is Dr. Gallenstein, and we have another lecture here today. This one is going to be on preferences and utility functions. All right, so we have just finished our math review, and periodically throughout the math review, I would allude to how all of that math would eventually become helpful for us as we explore and attempt to model economic decision making. Okay, but now that we're through the math review, now we're going to really put that into practice, and we're going to start relating the mathematics to how we can use it to model decision making. Okay, so we're really going to look at rational choice theory and the way that we take that theory and we build it into some math so that we can use the math to model decision making. This is going to be really helpful for us because we're actually going to use these models to study the impact, the theoretical impact of policies, of development related policies like conditional or unconditional cash transfers, fertilizer subsidies, the Supplemental Nutrition Assistance Program. We're going to be able to look at how policies might affect behavior by creating models. Okay. Now, to do that, we need to build from the ground up. We need to take the math that we've learned. We need to take the ideas and the insights behind rational decision making, as we talked about before, and we're going to put those two together so that we can create some equations that we can use to study this decision making. All right, so that's what we're going to do today. We're going to take the math that we've built thus far, and we're going to put it into decision making. All right, so let's get started. We're going to start with preferences. All right, we're gonna talk about how we can take preferences. All right, and we can kind of create some functions that capture the different components of preferences. Okay, so let's get started with that. All right, so what we're going to say is we're going to kind of formalize rational choice theory. We're going to formalize rational choice theory. Okay, we're going to formalize rational choice theory, and we're going to put in place three axioms. Okay, all right, so we're going to put in place some axioms. All right. There's other ways of going about these axioms, but I'm going to use these three because I think it's straightforward and I think it'll motivate what we're going to do. Okay, so here are some axioms. The first one's going to be completeness. Okay, the first axiom is completeness. The second will be transitivity. And then the third will be satiation, or more easily put, more is better. All right, so these are going to be the three axioms. These are going to motivate our mathematical model of human decision making. Okay, of utility, as we'll say. All right, we're going to take these, we're going to discuss them, we're going to use them to create utility function. Okay, we'll get to that next. All right, so let's talk about these each in turn. All right, so let's talk about these each in turn. Let's start with completeness. What is completeness? Now, remember when I talked about rational agents, I said that rational agents have they have well-defined preferences. Well-defined. What does that mean? What does it mean to have well-defined preferences? Okay, now for me to present exactly what this means, allow me to define some terms. I'm going to use some letters. Let's do blue instead. I'm going to use some letters, okay? I'm going to use the letters A, B, C, and D. All right. Each one of these letters stands for some good or some decision. All right, so let's just make kind of a trivial example. Let's say that A represents bananas. Okay, B represents apples. C represents cucumbers. And D represents potato chips. All right, just some random foods, okay? So all of these A, B, C, and D represent some possible goods that we can consume, and allow A, B, and C, D. They could be anything, but I just kind of created some random examples, some food items there. Okay, so what we mean when we say completeness, or what do we mean when we say well-defined preferences? What we mean is that agents have preferences. They have preferences. That means they have opinions about. They have preferences for all goods, actions, combinations of goods. Okay, so they have preferences for all goods. Now, how do we represent that? All right, I'm going to use some symbols here to represent what we mean by these preferences. This will be this. Ooh, that doesn't look very good. All right, let's see if I can. That's the symbol for strongly prefer. Here's the symbol for weakly prefer. Here's the symbol for indifferent. Here's the symbol for. Actually, that'll work. Okay. So strongly prefer, strong preference, weak preference, and indifference. Okay, so what I'm going to say here, what I'm going to present to you is that according to rational choice theory, what we are assuming that agents have well-defined preferences. That means that they are able to relate all possible goods and actions through some degree of preference. That means they can relate any of these goods one to another. All right, in some consistent manner. That means their preferences, what they prefer, is stable and well defined. So what do I mean by that? Let me present it. So what that means is that an agent has some preference about A and B. They might strongly prefer A to B. They might weakly prefer A to B. They might be indifferent between A to B. They might prefer B to A. But they have some preference. And that's my point. They have some preference. It's not uncertain what their preference is. So if it was uncertain, this would violate rational choice theory. Rational choice theory says they have some preference between A and B. So maybe they weakly prefer A to B. What do we mean by weakly prefer? That just means they either prefer or are indifferent between A and B. But they know that they either prefer or are indifferent between A and B. Right? Then they have these relationships. They know, rational agents know their preference between any pair of goods. So a rational agent will know their preference between any pair of goods. Okay, so if I put B and C in front of a rational agent, the rational agent would be able to tell me, oh, you know what? I prefer C to B. And if I put B and D in front of somebody, so let's say you put B and D in front of me. Do I prefer apples or potato chips? Well, I strongly prefer apples to potato chips. I have a defined preference. Maybe if you put C and D in front of me, maybe I'm indifferent. But it's at least well defined. I know that I am indifferent between C and D. I know that I don't care. I'm indifferent between eating cucumbers and potato chips. I'm indifferent. That means I have a well-defined preference. I know what it is. Strong preference, weak preference, or indifference. I'm not uncertain as to my preference. If you put A and B in front of me, I couldn't tell you I don't know. I would tell you either strong preference, weak preference, or indifference. All right, so this is what it means to have well-defined preferences. That means I have some preference between A and B, between all possible combinations between all goods. All right, so it's well-defined preferences. All right, so that is the completeness axiom. All right, so that's completeness. Now, all right, so that's completeness axiom. Let's get rid of that. Let's go to the next axiom. All right. just like in class. I have to erase the whiteboard. Okay. Axiom number 2, we have transitivity. All right, transitivity. What does transitivity mean? Now, this is really getting into the rationality. This is really getting into the rationality, and what I mean by that is that people's, or even say well-behaved preferences, all right, that means that their preferences are consistent with each other. So let me give you an example. This is what transitivity means. Let's say if an agent says that they prefer A to B, let's say, so they prefer A to B, okay, and they prefer B to C, transitivity says that it must be the case that they prefer A to C. This would mean that their preferences make sense. They're consistent. They are quote well behaved. They make sense. If I prefer A to B, if I prefer bananas to apples, and I prefer apples to cucumbers, well, then I must prefer bananas to cucumbers. Okay, this is well behaved. This is transitivity. Okay. If this weren't the case, let's say I preferred bananas to apples, and I preferred apples to cucumbers, and yet somehow I claimed that I preferred it wasn't well written, that I preferred cucumbers to bananas. If I said this, that would be irrational and violating rational choice theory. All right, so we're saying that preferences are well behaved. They're well behaved. All right, I'll show you more on that later. All right, so with that, let's move on to the last axiom. All right, let's just erase this just like a whiteboard. Axiom number 3, all right, it's going to be in blue. More is better. No satiation, non-satiation, we might say. That means you're never satisfied. You'll always take more of something. All right, now you can disagree with this, but what this means is that more is better. I always want more. I would always prefer 2 of good A to just 1 of good A. More is always better. For any, let's write this in some, yeah, well, this is good enough. All right. I always want more. I always prefer more of good A I always prefer more of good A as compared to less of good A. All right, more is better. All right, now, there we go. Pretty straightforward. Rational choice theory. We've defined our preferences. All right, now let's take those and let's take a step forward and then go into building our utility functions. And these utility functions are going to capture these preferences. So let's go to the next step. All right, utility functions. All right. Now, in the past, I primarily talked about agents trying to achieve the most of what they prefer. They're going to try to achieve the most. They want as much of what they prefer as they can, given their constraints. And what they prefer, let's say if someone preferred A to B, that means, and thus far I might have used the term, they get more, I might use the phrase subjective value, or we could say happiness, although that's not quite perfect, happiness, or pleasure. Okay, they get more subjective value, happiness, pleasure, whatever you want to say, from A than B. Okay, so straightforward. If they prefer A to B, that means they get more from A than they get from B. And it's up to them. It's their own valuation. According to their own valuation, according to their own preferences, they get more from A than they get from B. All right, that's all we're saying when we say their preferences. So what we want is a function that will communicate that. We want to create a function that will translate goods and actions. We want a function that will translate goods and actions into utility, into subjective value. So before when I said subjective value, just how much people value something or how much happiness they get from it, etc. All right, we're going to use a term called utility. All right, so people derive utility from consuming goods or doing particular actions. Okay, so they derive utility. All right, utility is is what economists use to describe kind of the subjective value, the happiness, the how much value you personally get from the decisions that you make based on your preferences. Okay, and this function, what we want it to do is we want it to take goods and actions and we want to map it into utility. So some function that's going to map it into utility. I want some function that will take a good or an action A as an input and it will spit out utility. That function, such a function, is going to be a utility function. All right, so we want this function, we're going to call this a utility function. All right, utility function, we're going to represent it like this. A utility function takes goods or actions as inputs and they give you utility. They give you utility. That means how much kind of subjective value someone gets from the good. Now, this utility function is interesting. The utility function is not giving you an exact number of someone's utility in the sense that utility is nebulously defined. There's no such thing as objective utility. What we're doing here is the utility function is giving us a way to compare between things. That is, I get more utility from A than I get from B. There's no point in trying to figure out how much, in some objective way, how much utility I get. Really, we use this utility function to give us relative measures between things. Okay. All right, so it's utility function. So now we need this utility function. We need this utility function to have some certain characteristics. Okay. Okay. Let me just go a little bit further. Okay. So this utility function is a function of some input. I'm just going to start calling it x. X is some. So x is a good. Usually it's a good. Or I like to say that also could be an action. And this utility function determines the amount of utility that you get from that good by consuming that good or completing that action. And so we would say that agents derive utility from X. So agents derive utility from X. Okay, now let's apply. So we need this function, and this function is going to be a mathematical expression. It's going to be a real function, so that we can work with it. Okay, and it's going to exemplify our axiom. So it's going to be complete. All right, what does it mean to be complete? Well, that means that this utility function is defined. That means it exists for all the relevant values of x. So the utility function exists for relevant values of x. All right, it's a function and it exists. That means it doesn't. Here, let me give you an example of a function that doesn't exist. Let's say if I tried to have a function. If I tried to have a utility function, it was 1 over x, then this would not exist if x equals 0. If x equals 0, it would be 1 divided by 0, and this is not defined. Okay? That means the function wouldn't exist. All right, so then this 1 over x does not work as a utility function because it's not defined. All right, so completeness. That just means, like I said before, completeness means that people have preferences for everything. That means that translates into a utility function by us saying that the utility function exists for relevant values of x. Okay, so it's complete. Transitivity. All right. Transitivity means that those same principles that we laid out before are going to apply for the utility function. That means let's say if I preferred A to B, that means that I get more utility from A than I get from B. If I prefer B to C, that means I will get more utility from B than I get from C. By transitivity, this will imply that I get more utility from A than I get from C. Okay, so this utility function allows us to capture completeness, and it allows us to capture transitivity. All right, so we need a function that is defined, it exists for all the relevant values of x, and a function that satisfies transitivity. Okay, that shouldn't be too hard, but let's go to the next step, and we're going to lay out a little bit more of what these characteristics need to be, what this utility function needs to be able to do. All right. Right now, just to be clear, what we're trying to do is we're trying to, in a sense, utility functions, they model rational preferences. And based on what we know about rational preferences, we want to be able to define a utility function that satisfies or that correctly models the rational preferences. All right. So, third axiom, more is better. All right. That means that as x goes up, u goes up. U of x goes up. Now that should look familiar to you. All right? As x goes up, u goes up. This should look somewhat familiar. All right? If I wanted to say, how does an increase in x affect or change u? Well, that should spark in your mind a derivative. All right? If I want to know how does u change given a change in x, I would take the derivative. So more is better. This axiom is captured by a utility function that's increasing. A utility function is increasing if the derivative is positive. U is an increasing function of x. So that means as x increases, u of x increases. All right, so this is a characteristic. That means that the derivative is positive. Okay, so here are some characteristics. Let's summarize. What are the characteristics that u of x needs to have? 1. U of x needs to be it needs to be defined. It needs to exist, or we could say defined. It needs to be defined for the relevant values of x. It needs to satisfy transitivity. I'll just write that, transitivity. And it needs to be an increasing function of the good or the action. All right, so the derivative needs to be positive. Okay, so then let's draw a graph of what a suitable utility function might look like. And maybe I'll even quiz you. Let me draw a couple functions and let's see what you think. All right, I'm going to use a bunch of colors here. This is going off to infinity. All right, there's a function. here's a function. All right. Okay. Here's a function. I'm going to put a whole bunch of functions on this board here, and we're going to talk about whether or not these functions will work as a utility function, whether or not they meet our characteristics, our basic necessary characteristics for a utility function. Okay, this next one is going to be, it's going to be like this. All right, it's going to start off here. Okay. All right, so here's a bunch of functions. I've got 4 functions here. And now let's go through our axioms and see what axioms satisfy these. Actually, okay, let's do, this is what I'm going to do. All right, we're going to go through each color. All right, so let's go through the yellow. Does it satisfy the various conditions? All right, so u of x must exist or be defined. Well, at this point, at this x, it's not defined. It goes off to infinity. All right, so it's not defined. This does not, x, so the yellow one does not satisfy the first condition. All right, and so the yellow one's done. Can't use it, not a good utility function. Whatever function that is, that's not a good one. All right, that doesn't work. Okay, so let's try the next one, red. All right, does red exist for all the relevant values of x? Yes, okay, so red checks out here. Transitivity. Is transitivity captured? All right, so let's try a couple things here. Let's say x1, x2, and x3. So x1, x2, and x3, does R capture transitivity? Well, let's say we know that they prefer x1 to x2. We know that they prefer x2 to x3. And so this function is consistent. x1 is greater than x2. You get more utility from x1. You get more utility from x1 than x2. You get more utility from x2 to x3. So then this should imply that you get more utility from x1 than x3. Actually, let me write this in utility terms. Okay, utility of x1 is greater than utility of x2. All right, utility of x2 is greater than the utility of x3. This implies that the utility of x1 is greater than the utility of x3. Is that the case here? Yes. Okay, is that the case here? Okay, so then this transitivity should be satisfied anytime the line, anytime the function is what we would call monotonic. That means it's always changing in one direction, so it's satisfied here. Okay. All right, so this one works for this one. Now what about it's an increasing function? Right, so based on non-satiation, or like I said, more is better, the function has to be increasing. It means as x gets bigger, the function should get larger. That means utility should go up. But the red line is going down. It's a decreasing function, so it doesn't work. Red is ruled out. So we can't do red. All right, so red doesn't work. Red does not satisfy what we need as a utility function. All right, so let's just get rid of red. Okay. All right, so let's go on. Let's do purple next. Does purple satisfy these conditions? Well, actually, we can answer that pretty quickly because all we have to do is look at it and see that it's not always increasing. It increases at first and then it goes down. That means it does not satisfy the third axiom, so it's off the table. We can rule it out right away. So let's just get rid of that. Now, we've got one left, and it's our green one. Does this function satisfy? It exists. Okay, check. Transitivity should hold. Check. And then It is always increasing. The derivative is always positive, so check. Here is a good example of a utility function. A utility function is going to look something like this. All right, it satisfies the conditions of a rational model of preferences. So then we're looking for functions that behave this way, that will act somewhat like this, okay, that will exhibit these characteristics. All right, well then let's discuss what are some examples of some utility functions that might satisfy these conditions. All right, all right. Okay, so what are some functions that might satisfy these conditions? Well, so a function that looks something like this is going to work. Okay, utility of x, it is positive, it's complete. So some good functions that we will use in this course are like the natural log or the square root of x. Now, in practice, economists, we use some more nuanced utility functions that will capture some other factors, but we're not going to get into that at this present moment. So here these are some good examples of utility functions that satisfy these conditions that we will look at in this course. All right. So with that said, let's continue. All right, so let's continue to talk about some more factors, some more traits that the utility function needs to exhibit. All right, so we've already talked about those basic axioms. All right, we talked about those basic axioms that it needs to satisfy, but actually we're going to impose some additional restrictions. Okay, so there's some very important characteristics that we also need to capture in this utility function. All right, so again, we're trying to write down a utility function that will satisfy. All right, so we have some utility of x. We know that it's going to satisfy completeness, or it's going to satisfy transitivity. It's going to satisfy more is better, aka we know that the derivative of the utility function with respect to x is going to be positive. Okay, it needs to have another characteristic. All right, and this is going to come from our intuition. So let's just say it right out, and then we'll formalize it and make it clear. So the utility function needs to exhibit a characteristic called diminishing marginal utility. Diminishing marginal utility. Why does a utility function need to exhibit this characteristic, and what does it mean? What does it imply? Well, let's talk about it for a second from an intuitive standpoint, and then we'll make it more clear mathematically what condition this implies. This will imply a certain condition. Okay, diminishing marginal utility. Let's use an example. Imagine that you're hungry, very hungry. Okay, I offered you a slice of pizza. All right, so you're very hungry, and I offered you a slice of pizza. And let's assume away any dietary restrictions. Let's say that you like pizza. All right. So I offer you a slice of pizza. All right. So first slice of pizza. Okay. I'm gonna be obnoxious here. Let's give some cheese on it. It's just basic, just cheese pizza. All right. Well, it's gonna have some pepperonis on it too. Well, we gotta get them right here. All right. Boom. It's gonna have some pepperonis on it. All right. So I'm gonna offer you a single slice of pizza. How much do you think you're going to value that slice of pizza? How much do you think you're going to value that slice of pizza? You're very hungry. This is your first slice of pizza. This thing, I'm going to represent value here by this. I'm going to represent it by green lines. All right. So this is going to have very large. This is going to be of very high value to you. All right. This first slice of pizza is going to be very valuable to you because you're starving. You're very hungry. But now, let's say I gave you, oh my goodness, we got to bring that size down. Okay. Let's say I give you, after you've eaten your first slice of pizza, I'm going to give you a second slice of pizza. Okay, this one's cheese only to save time. All right, I'm going to give you a second slice of pizza. Now my question to you is, how much are you going to value that second slice? Well, you'll probably still value it quite a bit, because one slice might not fill you up, but you're not going to value it quite as much as you did the first slice, because the first slice, man, you were really hungry. That first slice really hit the spot. The second slice, not so much. All right, let's give you a third slice. Oops, I need to change my size here. Okay, let's give you a third slice. So I give you a third slice of pizza. How much are you going to value that slice of pizza? Well, at this point, let's say these are big slices of pizza. And so by the time you've eaten two, you're not really that hungry anymore. And so, yeah, sure, you like the pizza, but you don't value it nearly as much. All right, now let's give you a fourth slice of pizza. Let's give you a fourth slice of pizza. How much do we think we're going to value this fourth slice of pizza? Well, at this point, you don't really value it very much at all because you're pretty full at this point. And so we have very high value here. So very high value here, less value, less value, less value. Now, do you think this is true? Pretty much for anything. Your first cup of coffee in the morning, you're tired, you drink it, man, that tastes good. And it wakes you up. Second cup of coffee, still good, still helpful. Not as helpful as the first, but still good. Third cup of coffee, okay, fine, we can probably do without it. Fourth, it's like, I'm not even sure if I want this cup of coffee anymore. So each additional unit of a good, each additional unit of pizza is worth less to you. It's worth something, but it's worth less. It's worth less. How do we capture that? So we would say that is a characteristic of consuming goods. The first, let's say let's say that I was walking across the desert, and I haven't had a drop of water in hours. I'm sweating, dehydrated. That first cup of water is going to be worth everything to me. But then if you were to, the 10th cup of water, it's not going to be worth as much to me, right? So could you agree that this is a fairly intuitive and important principle that really does capture the way that we value goods? The amount of value that we put on a good really depends on how many of that good we've consumed. If we've consumed 0 goods before, the first one's going to be very valuable. If we've already consumed 1, the next unit is going to be less valuable. If we've already consumed 2, the next unit is going to be even less value. If we've already consumed 3, the next value is going to be worth even less. All right? This is called diminishing marginal utility. How much utility do we get from one additional unit of a good? That is what's called marginal utility. Marginal utility is the amount of utility I get from one additional unit. Marginal utility is captured by the derivative. The marginal utility of x, or the marginal utility of pizza, this captures how much my utility goes up from one additional unit. My marginal utility of that first piece of pizza is going to be very large. So let's just call this x1, the first piece. The marginal utility that I get from this first piece is going to be larger than the marginal utility, that is, the additional utility I get from the second piece of pizza. And that's going to be even bigger than the marginal utility I get from the third piece of pizza. And that's going to be even bigger than the marginal utility I get from the fourth piece of pizza. I'm not sure if this is the best way to write this. Let me change the way I write this. So from the first piece, this is the marginal utility I get from the first piece, marginal utility I get from the second piece, marginal utility I get from the third piece, marginal utility from the fourth piece. Okay, So I get more marginal utility from the first piece than I do the second, and from the third, and from the fourth. That should make sense. The first piece is worth a lot to me. If I go from 0 to 1 pieces of pizza, that is a huge increase in my utility. If I go from 1 piece to 2 pieces, that's a big increase, but not as big as the first. How do we capture this in a utility function? How do I capture this in a utility function? Let's do it. Let's show how this gets captured in a utility function. All right. Diminishing marginal utility. So first, let's just draw a graph. I'm going to put 2 utility functions on this graph, and then we'll talk about which one exemplifies a utility function that has diminishing marginal utility. All right. Don't worry about them overlapping. I'm just putting 2 on the same graph, but they're not related to each other. Okay. In fact, there we go. All right. So I have the purple utility function. Okay. I've got the purple utility function, and I've got the green utility function. Now the question is, which one of these does a better job of capturing utility, of explaining utility? Well, let's look at the purple one first. Actually, let's look at the green one first. All right. First, does it satisfy completeness? Let's use green. Completeness, okay. Transitivity, okay. More is better. The derivative of the green utility function is positive. All right, so that makes sense. It satisfies that. Great. But now, what about this diminishing marginal utility? That means the marginal utility should be higher at, let's say, x1 than it is at x2. The more x I have, the lower the marginal utility should be. Well, let's take a look at this graph. This is a straight linear line. That means the slope, the derivative at this point x1, that's not the best way to write it. The derivative at x1, okay, is a straight line. The derivative at x1 is equal to the derivative at x2. Okay, the derivative at x1 is equal to the derivative at x2. Because it's a straight line, it has a constant slope throughout the whole range. That means it has constant marginal utility. The marginal utility from the first piece is equal to the marginal utility from the second. That would be constant marginal utility. This would be constant marginal utility. That doesn't work because we need diminishing marginal utility. That's not good. So the green doesn't work. It doesn't satisfy. It doesn't do a good job of modeling utility. What about the purple? With the purple one, it's kind of a purplish blue. Does it satisfy everything else? Sure. Okay, great. The derivative is positive. Excellent. But now, let's think about its value at x1 and its value at x2, or the value of the derivative. All right. The marginal utility at x1, if we just look at it, the marginal utility at x1 is greater than the marginal utility at x2. This checks out. This exhibits diminishing marginal utility. The marginal utility at x1 is larger than the marginal utility at x2. That means I get more additional utility from the first unit than I get from the second unit. Okay, so this purple curve is going to satisfy it. Now, how would I communicate this property in mathematical terms? All right, so now I'm going to go back. Let's do some erasing here. I'm going to erase all this. Now we know which one we want. Okay, I accidentally erased my axes here. I'll bring them back. All right, so this doesn't work. All right, let's bring back the axes. All right, so now what characteristic does this need to have? What mathematical property would capture this diminishing marginal utility? Can anyone think of it? Think back to our math lectures. In our math lecture, we talked about concave functions and convex functions. What does this function look like to you? Does it look concave or convex? It would be concave. What do we know about concave functions? We know that the second derivative, is what? Negative. So there we go. We're piecing together properties of a function that will do a good job of explaining or of modeling rational preferences. Okay, so we're building our toolbox. We need a function that will be complete, a function that will satisfy transitivity. We need a function that for which the derivative is positive. And now we have an additional property. We need a function where the second derivative will be negative, so that it will exemplify diminishing marginal utility. All right, then this model, we can use this model to do a good job of presenting or modeling rational preferences. Okay, so then let me just summarize all of this. I'm going to erase everything. Let me summarize all of this. Utility function. Utility function. All right, utility function. We want a mathematical expression. We could say expression. More importantly, we say a function, a mathematical function that captures or models or represents rational preferences. Okay, we want a function that's going to represent rational preferences. All right. This function then should exhibit some characteristics. One, it should be complete. Two, it should satisfy transitivity. Three, the derivative of the utility function should be positive. More is better. That means as I get more x, my utility goes up. It also needs to satisfy the second derivative needs to be negative. Say diminishing marginal utility. Okay, so we want a function that's going to satisfy these properties. And then we can use that to model decision making. Because if this function does a good job of capturing rational preferences, then we can use it to study decision making. Because remember, we are assuming, according to rational choice theory, that agents make decisions based on their preferences. Furthermore, we know that agents, what they do is they choose. Let's do that. They make choices to maximize. So far I've said maximize like their subjective value, how much, they want to get as much of what they prefer as they can given the constraints. So what we're going to say is they make choices to maximize utility. All right. So then we can now use this utility function that exhibits rational preferences to model the behavior of rational agents. Rational agents. All right. So this is going to be a powerful tool. So this is a utility. These are utility functions. All right. Okay. Now, I think I'll stop this lecture for here, and then I will save indifference curves for the next lecture. Thank you very much. I hope you have a great day.